Okay, let's start the first day of the conference. The first speaker this morning is Professor Jiahao Cheng. The title is The Deformation Formula of Quantum Dynamical and Baxter Equations of a non-abelian base. Please.
Thank you. I would first like to thank the organizer for organizing this great conference. My great honor to be here, and this is a very wonderful place. Today I will talk about deformation formulae associated with quantum dynamical Young-Baxter equation over a non-abelian base. So let's recall some background about this equation. Okay, let's first recall a formal star product on a Poisson manifold. Is a formal associated deformation of the algebra of smooth function. So to deform the algebra of smooth function, this is a commutative algebra. So we deform it into a non-commutative but still associative algebra. So the question is that suppose that we have a Poisson manifold, and can we find a star product such that the classical limit of the star product is the given Poisson bracket? So, okay. Also, this question has been widely studied. So, in the sympathetic case, this case is resolved by the Wilder, Lecommon, and Felder. And in the general Poisson case, so this question is resolved by Conservatory, and also from quantum field theoretical viewpoint by Cattaneo and Felder. And there's many people start this topic. Okay, and quite parallel to this story, Drinfel'd introduced the notation of quantum group, and he started the theory or deformation, start to consider deformation of Hopf algebra. And in particular, one can obey a special type of star product by certain universal deformation formulae. So the situation is like this. Suppose that we have a smooth manifold, and with an action of a Lie algebra G. And suppose now that we have an element F belong to, here UG is the universal enveloping algebra of the Lie algebra G. So we have an element F belong to UG, tensor UG, okay, with some formal parameter H bar. And suppose that F satisfies the following equation. So, okay, the last equation means that so up to a higher order of H bar, so F is just some kind of identity map, so or just corresponding to the Eulerian multiplication. And if you such element F is called a Drinfel'd twist. So if one has a Drinfel'd twist, then one can define an associative product. A new associative product on the algebra of smooth function. So by this formula, so here we write F equal this actually is taking some F1 tensor F2. This is the Sweden notation in Hopf algebra, and then we use F1. So we may think F1 as some kind of differential operator on the function F. And also F2, so S on G by differential operator action. So and then you get a new star product, and this equation ensure that so you really has a associative product. So the product the multiplication is associative. So okay, this is one way that one can obtain some special type of star product. So if one is in such a situation, and actually, this is so when they want to ask that how this is this an effective approach? So when they want to study this, so if this approach is effective, so easy for calculate. So and there is an iterated approach to write down an explicit universal deformation formula, not start with okay, we write down a star product using this f, but this f is some kind of quantized object, so it has been quantized. So the question is that suppose that we begin with classical triangular R matrix. So this has not yet been quantized. So can you can you just begin from a classical triangular R matrix? Can you write down the star product? So in such a way, Okay, so okay, and then usually people start this story by the approach of Felder's. So here nowadays there's many generalization of Felder's approach in the symplectic case to solve the deformation quantized problem, and these four people, Dolgosov, Isawa, Niyakovich, and Safarov, they many years ago they wrote a paper and they explain that so actually this universal deformation formula approach can apply to a more general context beyond the symplectic case. For example, we can include some irregular partial structure. So in this story, Okay, so then later in this talk, we will generalize the result to, because they just consider classical triangular R matrix. So later in this talk, we will generalize their result to, or their method to triangular dynamical R matrix. Okay, let's recall more background. So Professor Ping Xu, he introduced the quantum dynamical Yang-Baxter equation, or called the GNF equation, over an abelian base. So let's recall what this is, what this equation looks like. So now suppose that G is a Lie algebra and H is a Lie subalgebra of G. But now H is not necessarily an abelian Lie algebra. So not necessarily an abelian Lie algebra. So this is why we call over the non-abelian base. So because H is could be non-abelian. So now then we take a vector base. So this is a group of vector base Hi of this vector space H, and we take lambda I to be the corresponding okay, this Hi corresponding to some kind of linear function on H star, the dual space of H, and moreover we take Ci to be the dual base to Hi. So we just fit some notation. So fit some notation. Okay. So any questions? Fit some notation. Just okay. Okay. Now then we consider a map looks like this. So R is a map. So this from a space H star, so the dual space of H to UG tensor UG with some parameter H bar. So this we regard as once we regard as a very linear map, so between the two space, in particular case, R is not necessarily defined on the whole H star, so maybe just defined on some open subset of H star. And in particular case, one may require this map to be smooth or memomorphic, or depends on the context. So in this talk, we will just omit this aspect. So we just regard it as a map from H star to UG tensor UG H bar. So we require that this map is H bar equivalent. Here we can see that on the left hand side on the space H star, the Lie algebra H. So here H can be a non-abelian Lie algebra, right? So H can act on H star by adjoint action. So then we can take a Lie derivative. So if that is adjoint action. And on the right hand side, then you have the commutator. Wow. So here Hi just take the basis vector of the vector space H, and lambda is the coordinate on H star. So okay, then here, well, we will treat R as an element on this space. So this is the tensor product of three guys, right? So this okay, but here we have to attention that because now H is an abelian Lie algebra, so we know that. So let's look at function on H star. So if one first does look at polynomial function on H star, then the polynomial function on H star is the symmetric product of Hy. And we know that there is a PBW theorem says that the symmetric product of H and the universal enveloping algebra of H, they are as a vector space, they are isomorphic. Actually, they are isomorphic as a co-algebra. Right? So, and we know that there is a non-communicated multiplication on UH. Right? So then, by this isomorphism, we obtain an non-commutative multiplication on the symmetric product of H. So this is just a polynomial function of H star, right? And we can extend. So in this case, we can extend this non-commutative multiplication to the whole space of the smooth function on H star. Okay, so this is what we call the PBW multiplication. So actually, then we just think that H star has been deformation quantized. So, okay, and then now, okay, we have an element R here, and then now we can have the nonabelian quantum dynamical Yang-Baxter equation in this following way. So here we know that R is some kind of function of lambda. So R has some component belongs to this factor, right? But this factor is endowed with the PBW product. So this is non-commutative product. So this equation, you see that in everywhere you need to take the function multiplication, you take the PBW product. So this equation is well, complicated equation. Where H is just an abelian Lie algebra, then it just back to the more back to the abelian quantum dynamical Yang-Baxter equation. Yeah. That's right. Yeah, the PBW product here. Yeah, here also. Yeah, here also a product here. Oh, thank you. Yeah. Okay, and we can look at the classical limit. So the solution of this equation, then it is called quantum dynamic R matrix with capital R, and then we can take, of course, we can take classical limit. So when one take classical limit, you can define this small r lambda. So you find that this small r lambda also satisfies some equation. So then we get back the nonabelian classical dynamical Yang-Baxter equation. So the one important question is that suppose that we have a classical R matrix, classical dynamic R matrix. So how we quantize it to get quantum dynamical R matrix also. This is in general, not an easy question. Okay, now we look at one way to solve this non-abelian quantum dynamical Yang-Baxter equation. This is a standard way, actually. So suppose that we have another map called F from H star to UG tensor UG H parameter. So okay, we also assume that this F map is an H equivalent map. So okay, and it satisfies another equation called the non-abelian dynamical Twix equation. So it satisfies this equation. So this equation looks just a little bit simple compared with the equation for R. So okay, satisfy this equation, and the point is that if you can find a solution F of this equation, satisfy this condition, and then you can reconstruct an R by such a way. So this is also standard way. So you can reconstruct R by this way, and this R will satisfy the quantum dynamical Yang-Baxter equation. So then we can, okay, this is one way to solve this quantum dynamical Yang-Baxter equation. Okay, then now we look at some result. We call some result. Here we take G to be a Lie group of the Lie algebra G. And we just mentioned classical dynamical R matrix. So to this classical dynamical R matrix looks like this. And so suppose that you have a map looks like this, and then you can define a two-vector field. It contains three components. On where? On H, sorry, here is H star, the Lie algebra H. On H star times G. So here is Lie algebra H, not H bar. So, okay, so here pi H star is the Lie Poisson structure on H star. So, because H can be a non-abelian Lie algebra. So, and here is a cost term. So this is a standard term, right? So here lambda I and hi are the sum standard base that we have specified before. Here hi, this arrow means that so hi S on G by left invariant vector field, and here R, this arrow means that R lambda S on also S on G by left invariant vector field. Okay, so whenever you have such map R, then you have a two vector field pi on H star times G. So a theorem of Xu says that so R is a dynamical, classical dynamical R matrix if and only if means that you need to satisfy the classical dynamical equation, right? Dynamical Yang-Box equation. If and only if pi R is Poisson structure on X star times G. In particular, she studied a very special type of classical dynamical R matrix. So this is, one see that this is a Poisson structure on X star times G. So one may ask that when this Poisson structure comes from a symplectic structure. So okay, so then we now introduce a concept. So if this Poisson structure is actually a symplectic structure, then we just call it a symplectic triangle dynamical R matrix. So this is very special kinds of triangle dynamical R matrix, classical.
Just some clarification. So there is no, as to my understanding, there is no canonical Poisson structure on H star. They are modular in KCB, for instance. They are modular of bundles. Right? So anyway, like KCB, E times elliptic curve times E times E. As to my understanding, there is no canonical structure. It is not co-contained bundle. But do you consider any Poisson star structure? Or there's some specific one which are geometric?
As we have fixed some bases, we have choose some bases of the vector space, so then we can have one.
Is it some kind of canonical one, or exemplar? Any star structure for B, for the dual forms?
I think this is canonical. Lie Poisson on X star. Where Cij? Oh, Cij is the structural constant of the Lie algebra H. So once you have choose a base. Can be non-abelian. So
it is not like for KZV we have parameters we have from those, right? Now it is different.
Okay, thank you. Okay, next we call more theorem. So Professor Xu proves that when H is an abelian Lie algebra, so when H is an abelian Lie algebra, so and any symplectic classical dynamical R matrix can be quantized. So this is his result. And moreover, Alexev and Clark, they moreover prove that when H is a non-abelian, so for any non-abelian but still symplectic triangle dynamical R matrix, also can be quantized. So both they will use a lot of Felder construction. So this they prove that they can quantize, but they're very complicated. So complicated formulae. Wow. Okay, let's recall another viewpoint on the non-abelian dynamical tweaks. So suppose that we have a F. We have a F which is a map from X star to UG tensor UG. Okay, we suppose that it satisfies the non-abelian dynamical Twix equation we just mentioned before. And if you have such F, then you can actually define a star product on H star times G. So you can define a star product which satisfies this condition. So we satisfy the condition. For example, if you have two functions with variable on G, right? Then you can just use F to S on F1 and F2, because F you can regard as a differential operator with two entrances, right? So okay. So this condition uniquely determine a star product. So we call this star product a compatible star product. So also in particular, if you have two functions with variable lambda just belong to H star, then just back to the PBW product. Okay. But one has attention, one has attention that you can see that this star product is not symmetric with respect this variable. So you can see the formula. Fx times G lambda just equal the UNE multiplication, but G lambda times Fx equals something complicated, right? So this is not symmetric with respect these two variables, right? So this cannot be wire ordering. So we just make a remark. So just make a remark. And the point is that here the point is that if one want to solve the quantum dynamical Yang-Baxter equation, then one can try to find out the solution of the dynamical twist equation. And the dynamical twist equation, the solution of dynamical twist equation, just corresponding to some special kinds of star product on, so we call it compatible star product on H star times G. So this is Xu's view of point. So okay, here we propose the question. So after introducing many background, so when H is an abelian, in this case, well, one can consider near algebra. So the base manifold is H star, and here we put it T H star, the tangent bundle, and direction G. So here G is trivially on H star. So we require G as trivially on H star. And in this case, Professor Xu construct a Twixer. So a Twixer means that this is an element belong to the tensor product of two half of algebra. We will just record it, all this definition. And here F, the construction of F looks like following. So curly F here equal F lambda. So this is the dynamical Twix times the capital theta. Here capital theta equal the exponential of this guy. So this guy. Okay. So and from this Twix curly F, then we construct a quantum groupoid. So this is some kind of half of algebra. Half of algebra. We will just record the definition. And moreover, we can see that the co-multiplication of this half of algebra, this quantum groupoid, satisfy this relation, right? So we may just in such a way we may just think that we have translated the solution of the quantum dynamical Yang-Baxter equation into some kinds of half of algebra object. So this is the quantum group approach. Right? So now we ask two questions. So the first question is that if H is an non-abelian Lie algebra of G, and suppose that R lambda is suppose that you have already a non-abelian quantum dynamical R matrix. So in this case, can one still construct some kinds of quantum groupoid? So in the sense of Xu, so when H is abelian, then you have a construction. Well, so given by this formula, so each term is explicitly so right. So but when H is non-abelian, so can one find also construct a quantum groupoid? And the second question is that even you have this R lambda, so this R lambda is very complicated. Well, so can we just mentioned that so in the situation that if you have manifold M with action of Lie algebra G, well, then you have a universal deformation formula to keep a star product, right? So here the point is that R lambda is usually quite difficult to obtain R lambda. So So suppose that you begin with sympathetic triangulate dynamical R matrix, which means that this can be quantized. So can you just use this R lambda, so classical dynamical R matrix data to write down the universal deformation formula? So to write down the star product on M. So this is our question. Okay, so let's quickly recall the definition of quantum groupoid in the sense of Xu. So a quantum groupoid is so first it contains an associative algebra with unit, and it has two. It's over a base ring R, so R can be non-commutative, right? So it has two maps called source map and target map. So the source map is R to H, it's an algebra map, and the target map is the opposite algebra of R and maps to H, so it's also algebra map. And require the image commutated. And when you have this source map and target map, you can define R by module on H. So left R module and right R module on H by this formula. So by this formula. Okay, so in particular, here we can take, because H is an RR by module, so we can take tensor product. So here on the left hand side we use YR module structure, and here on the left hand side we use the left R module structure. So okay, the third condition that we have a co-product delta H to H tensor H satisfy this condition. Okay, and moreover we require that we have unimap. So one easy example of quantum groupoid is if you want to take a Lie algebra point over a smooth manifold, and then one can consider universal enveloping algebra UL of the Lie algebra L. So you can show that this is a quantum groupoid. So and the source and target map, just the inclusion map. So just inclusion map. So okay. Okay, now we call a very important concept called twixtor. So this is some kind of Drinfel'd twist in the but in the setting of with base manifold M. So suppose that you have element F belong to H tensor H. So here's H outside. You for F satisfy this equation. So the first equation we have seen before, and the second condition that says that F is inversible in some sense. So and if you have such twixtor F, and then you can define a new Hopper algebra point. So you can just use F to twist the structure of the Hopper algebra that you have. So now we have, suppose you have a twist, then you get a new quantum group point. So here the multiplication and the co-unimap are the same one, and we deform the co-product, the source map and the target map, and in particular, if R1 and R2 belong to the base ring R, then we can just deform their multiplication in such a way. So you can see that this is just the prototype of star product. The universal deformation formula of star product. So okay. So now look at back to our question. So now suppose that H is an nonabelian algebra. So in this case, we have to mention before, H acts non-trivially on H star by the adjoint action. So now we remember H can act on H star. And moreover, H star here we just regard it as vector space. This is abelian algebra H star. But H star can also act on the manifold H star itself. Suppose that you have a dual base CI here, then you just make dual base to the derivative to take the vector field of taking the deviation with respect the I, the here lambda I, the coordinate. So here H star, so even he is abelian, so he can act on the manifold H star. So then one can just think about that actually the pair H and H star is a Lie algebra, so you can take its Drinfel'd double. So DH, so the Drinfel'd double, okay, as a vector space, it's just H plus H bar, but it has a non-trivial Lie algebra structure. So DH, the Drinfel'd double, is also Lie algebra, and the two action of H and H star we mentioned before just extend to the Lie algebra action DH or H star. Okay, now you have an Lie algebra action DH or H star, then you can consider the action Lie algebra. You can consider an action Lie algebra, and you can see that this action Lie algebra associated with this Lie algebra action just equal th star direct sum h as a vector as a Lie algebra over h star. So okay. Okay, and we know that, so for the Drinfel'd double, well, we have a canonical R matrix. Well, we have a canonical R matrix here, but now this canonical R matrix, because DHS on the basic manifold X star, so this canonical R matrix, if just S on X star times the see here, capital H is the Lie group of H. So this R matrix S on this basic manifold X star times H looks like this. Wow. And it just, if we identify X star times H with the cotangent bundle of H, so this Poisson structure is just a symplectic, just corresponding to symplectic structure of this cotangent bundle. And in a paper of a group, she has given a quantization of this symplectic structure on the cotangent bundle of a Lie group. So, and this her quantization is actually a compatible star product. So, with corresponding to theta tilde. So, these tricks belong to the two complete tensor product of this Hopper-Field algebra. Well, okay. And now we assume that G has a decomposition. So, decomposed as X direction M. Here, the M is preserved by the H action. We call this a reductive action. And if G has this decomposition, then you can define Lie algebra, which is TH star times G. Here we have extend the action of H on H star to the action of the whole Lie algebra G, which is require M S on 0 on H star.
Is it supposed to be a subalgebra or subspace?
Subspace. Okay, so with this assumption that you can construct a new Lie algebra, which contain TH star divide sum H as a Lie subalgebra. Okay, and then we can state our theorem, that the first theorem which says that suppose that you admit a decomposition H direction M satisfy the condition that we mentioned before. So this condition ensures that TH star times G has a Lie algebra structure over H star, and then you can consider the universal M looping algebra of this algebra over H star. And suppose moreover you have a dynamical twist F from X star to UG tensor UG H bar, then now you can consider a twist F tilde. So is equal to F lambda times theta tilde. Here theta tilde is the deformation quantized of the cotangent bundle of H. Okay, then one can prove that F will satisfy the twist dynamical equation if and only if kernel F is a twist in this quantum groupoid. So the proof relies on some result of Dorling and Murdoch. So on dynamical cocycle. Okay. So these are our first result. Then we construct the quantum groupoid where H is non-abelian, and we can moreover in this case we can write a universal deformation formula. Suppose that M is a manifold and G is a Lie algebra which is on Tm by rho. So this is a Lie algebra action, and as we have just mentioned before, we have construct F tilde. Then once you have F tilde, and then you can use rho time tensor rho to map F tilde to be an operator on the space H star times M. So here M is just arbitrary manifold with G Lie algebra G action, and in such way, by such formula, we call it universal deformation formula. You get certain kinds of star product on H star times M. Sorry, here it should be times M. On H star times M. So this star product also satisfies this special property. So in this sense that we find out the universal deformation formula for the dynamical quantum groupoid. So in this case, okay, then let's look at the last question. So we just mentioned that even you can find the f lambda, so it could be very complicated. So you can complicated write down the explicit formula of the star product, right? So suppose that we just begin by the data of a symplectic triangular dynamical R matrix. So this is the classical dynamical R matrix is symplectic. So we know that this guy can be quantized to a quantum dynamical twist, right? So the point is that we don't know the explicit formula of f lambda, right? So here what we want to do is that we just use the data of R lambda to get to write down the f lambda. So let's look at this. So let's look at how to do it. So now suppose that we already have a symplectic triangle dynamical R matrix R lambda, and then we have defined a Poisson structure, right? Or define a Poisson structure. Actually, we know that this Poisson structure is symplectic, right? So it's undegenerated because it requires R is symplectic. So this Poisson structure is symplectic. So it corresponds to a symplectic form. So we can take the inverse of pi r, then you get a symplectic form. This is the red product of the two copy of this Lie algebra over x star 2k, right? So this is a two-code cycle. Once you have a two-code cycle, a code two-code cycle, and then we can actually define a Lie algebra extension, but define the Lie algebra extension in such a way. So here the center we just put it a case, the base field can be real number or complex number, and x bar is a parameter. So it's a base of a one-dimensional vector space. So and the Lie blank on the extension is given as follows. So here we just this y alpha to be the base of the fiber vector of this Lie algebra, and then the Lie blank on the extension L just looks like following. So here we can see that in here we add the parameter h bar, and here we add the centralizer. So to this term, the take value on the h bar. So h bar. Okay. Then we construct a Lie algebra control a new Lie algebra over h star. So over L here is over the base manifold h star, and so we can take the universal M looping algebra of this Lie algebra over h star. Right, but you can see that this guy should be very huge. Let's look at what it contains. Well, it must contain some part of here, right? Some part comes from here, but also some parameter h bar. Actually, the universal M looping algebra of L contain many power series of h bar, right? Contain many power series of h bar. Okay, now since this is a universal M looping algebra, it is associative algebra, right? So it has a natural associated multiplication, which is denoted by this circle. So this has a natural multiplication of this universal M looping algebra, and then here we UL here we tensor with the smooth function on a manifold M. So right, and then we define a theta map. So here the map theta is just send all products of vector y alpha in UL to 0. Here y alpha, what is y alpha? We call what is y alpha. Y alpha is vector, it belongs to here. So just take all vectors here to 0. And then you can imagine that what you remain. So you remain some you must remain some function, right? But also some formal power series of h bar. So wow. So this is what people call simple map. So simple map. Okay. Oh, here and now here now suppose that M is a manifold with a Lie algebra action G with a Lie algebra G action, and now then we can just have a map rho here. Let's look at, because G here we can see that G S on M, right? G S on M, and this guy contains Tx star direct sum H, right? Tx star direct sum H S on H star, right? So actually you have a morphism of between this two Lie algebra over X star. So here the Tx bar is as trivially on the right hand side. Okay, with this data in hand, then you can define the trivial operator delta. So delta is operator from UL tensor C infinity M to itself. So the explicit formula of delta given as follow. Here we have used symplectic form corresponding to the symplectical dimensional R matrix. Here, rho y alpha is just this Lie algebra action map. Here we use the commutator of y alpha with A. So here the commutator is taken with respect the lateral multiplication circle on UL. Okay, define such operator, and the good news is that finally we have such film. We just define an operator delta, right? So now we can use this delta to define something. Suppose now that f and g are smooth function on M, on the manifold M, right? And then you can, then you can, of course, you can regard C infinity M as a subspace of UL. Well, you can, of course, regard it as a subspace of UL tensor C infinity M, right? And then you use delta to S on this function on M, smooth function on M, right? Then you get something new, right? You get something new. Then you get something new on the right-hand side, but in this case, it could contain some component in UL, right? So in UL. So, and here you take the exponential of h bar delta, right? So you can see that this guy will belong to UL with many factor, many y alpha factors, so, right? And then since this guy belongs to UL, you can just take their multiplication in UL, and then you send all this y vector to 0. Then you take this sigma map. Then it maps all these things back to C infinity M, tensor with the formal parameter h bar, the polynomial of formal parameter h bar. Okay, so then, okay, what we get? So what we get is that by such formulae, we actually use this delta operator. We actually define an F map from H bar to UG tensor UG H bar. So just use this operator delta. You can define such F map. And the good news is that let's just recall what is the delta. So to define delta, you have to use this symplectic structure. This symplectic structure, we call that this symplectic structure contains what? Contain this dynamical R matrix, right? Classical dynamical R matrix. So the operator delta is closely. So it is produced by the classical dynamical R matrix, right? So okay, and then finally by such formulae, you define F from H star to UG tensor UG H bar. So and one can prove that. So if you begin with a classical symplectic dynamical R matrix, then you can prove that F actually satisfies the non-abelian quantum dynamical twist equation. So in some sense, we just directly construct the quantize of the symplectic dynamical R matrix R lambda by such formulae. So this is our second main result. And once you have constructed this F lambda guy, then you times with the capital theta tilde, right? Then you get the twist kernel F of the desired quantum groupoid of this solution of the non-abelian quantum dynamical Yang-Baxter equation. So thanks. So.
Thank you. Any questions, comments?
So you've given a very uniform approach for any subalgebra satisfying this direct sum condition, right? G is H plus A. But would you kind of suggest that some subalgebras are more interesting that we should focus the study on, apart from the abelian ones? Are there some interesting examples that have nice geometric interpretation, or?
Actually, we are looking some new case that has not yet been studied by people before. We are just still looking for. Yeah. So yeah, we are trying. So, yeah.
It is really new to me. What is the point? The point is QDYBE, dynamical R matrices. What are exactly these lambdas, right? They are from Picard. basically, right? From Picard. Well, unfortunately, they involve modular of curves too, but for elliptic curve, just Picard here, right? No, normally, with some stretch, maybe vector bundles, but I don't know the theories here. This will be very nice if you have some kind of Picard or whatever with some canonical Poisson structures, then you immediately introduce star, and then you will have very interesting geometric theory. But as far as I can say, there is no canonical structure on Picard, right? You need to consider Hitchin system or something. This can be some kind of approximation. But your question is very good. Do we have some kind of examples which are more geometric than others? For you, it is pretty much arbitrary factorizable G with triangle decomposition, right? But maybe there are some which are from geometry, from some canonical symplectic structures. Cotangent bundle never appeared in QDYBE, as to my understanding. I may be completely wrong, but it seems that it is just new direction, you know, right? Not something connected with what we know from because of QDYBE, because of QZ equations for arbitrary curves or arbitrary genus, something like this. Okay, thank you. Just a comment.
Thank you.
You, right?
I just wondered about existence of classical R matrix.
Okay.
And now questions about Poincaré-Bergov with basis. Basically, it depends on choice of irreducible representation of element of maximal length. Okay, in this case, maximal element in symmetry group. And do you know something about transition matrix between two different choice of Poincaré-Bergov with basis?
I need to think about this also. Okay. So maybe we discuss more later. So, yeah.
Any other questions, comments? We still have time, but okay. Let's thank the speaker again.
Oh, thank you.